Hello, y'all. Welcome to lesson 68 of my DP chemistry curriculum. Today we're doing reactivity 1.2.1. We're going to talk about bond breaking, how that absorbs and bond forming releases energy. So we'll be able to calculate the enthalpy change of a reaction from given average bond enthalpy data, which we'll actually find in section 12 of our data booklet. So when we go into this, what we need to know is that bonds are pretty much magnets. When you think of a magnet, and you spell it right, possibly. When you think of a magnet, you think about two things together, and they're probably attached. Maybe we'll just use some bar magnets, north, south, which kind of represents the electromagnetic pole between them. Now, if you want to pull two magnets apart, that takes a lot of energy. What that tells us is that to break a bond or bond breaking, that must be endothermic. We literally have to apply energy to break that bond. Now, furthermore, if you have your magnets and they are going to collide because they're pulled to each other, that might make a snap sound. There's these magnetic toys that make fun sounds when they collide. And that sound is just displacement of air particles, creating that pressure wave that we hear a sound, meaning energy must be released to do that. Therefore, bond forming, like magnets coming together, must be exothermic. So we can see the release or absorption of energy based on what's happening to the bonds. We determine this and we actually call this field of the energy of the bonds as bond enthalpy. Bond enthalpy. And basically, we look at all reactions as the breaking and forming of bonds, because that's all they are. If we think about a reaction that is overall endothermic, we'll notice that the products have bonds that have higher energy than the reactants. These would be less stable products. Furthermore, a process that is exothermic, our products would have less energy. So these are our energy diagrams. Energy. These would be more stable. And we can determine this by the energy within the bonds. Again, we can get these values from our data booklet, and we'll do some examples showing that in a little bit. So how do we get these values and how do we quantify this? Well, to quantify the energy required to break bonds, we use what we call bond dissociation energy, which is just bond enthalpy. Bond dissociation energy. And what this actually means and what bond enthalpy means is really just the energy required to break 1 mole of bonds in gaseous molecules. Very much like ionization energy, this is all based on 1 mole in the gaseous state. We don't want to have to deal with any other forces or any other molecules interacting. So that is exactly what we are quantifying when we look at our section 12 of data booklet values. The big thing that we do have to realize is that all those values, and I'm just going to write here, section 12, all these bond enthalpy values These are average values. Now, these are average across many different things because we could have H2O, which has one type of oxygen hydrogen bond, but we could have methanol, which has another type of oxygen hydrogen bond. And these bonds are going to have different amounts of energy. We cannot equate them. So that bond right there is going to be very different than this bond right here because of the way that electronegativity works and electrons are pulled one way or another. They will have different strengths. And so to quantify bond enthalpy, we have to take average values. So they're never exact. Now, that is one key aspect that the DP will definitely require you to state at some point in another when they're making you do calculations of enthalpy. So with that said, let's do some calculations right now. Enthalpy of reactions from bonds. So what we really need to understand is that the reactants, those are going to be breaking bonds. Meanwhile, the products, those are going to be forming bonds. And what you'll notice is that all our bond enthalpy values in section 12 are positive. But if we're forming bonds, those need to be negative because it is the opposite function. Therefore, when we do this, we can look at delta H, or the change in enthalpy overall, is going to be equal to the bonds broken. And we're going to do minus the bonds formed because we're going to get that energy back as they form bonds. So when we write our real equation, and this one is not in your data booklet, so you need to make sure you understand it, it is the delta H of the reaction is equal to the sum of the reactant bond enthalpy minus the sum of the product bond enthalpy. All right, with all this stuff said and done, we can now do our first true example. So we'll start off with something simple. We have hydrogen gas plus fluorine gas reacts to form hydrogen fluoride. Now, we do have to balance this, and we'll notice that we are creating two molecules here. When we look at these specifically with Lewis diagrams, we can see we have one hydrogen-hydrogen bond, one fluorine-fluorine bond. But because we're making two hydrogen fluorides, we have two hydrogen fluoride bonds. And so as we calculate these, I'm going to put my reactants on one side, and it is the enthalpy of hydrogen bond to hydrogen plus fluorine bonded to fluorine minus 2 times hydrogen bonded to fluorine. So getting these values from my data booklet, I get 436 kilojoules per mole plus 159 kilojoules per mole. And I'm going to subtract that from 2 times 567 kilojoules per mole. This will give us a net energy change of negative 539 kilojoules mole inverse. And that's how you do any one of these reactions. Now, on your DP exam, you may see something a little more complicated. So let's go ahead and try one of those more complicated reactions. In this one, we're going to do ethene, which is C2H4, plus hydrochloric acid, HCl. We're going to keep these on our gaseous state so we can refer to our bond enthalpy values. We're going to react this to produce chloroethane, C2H5Cl. One of the best things to do is draw these out so you can see what each bond looks like. The only way to draw this diagram looks like this. Normally, you may have these diagrams already provided to you, unless you are later in the curriculum where you are able to draw them yourself. So there is our ethane. Then all we have to do is break that double bond, put a hydrogen on one end and a chlorine on the other. And we can start analyzing our bonds. So first I see the carbon-carbon double bond. That's different than a carbon-carbon single bond, so we'll have to make sure we keep that very clear. Then I see 4 times our carbon-hydrogen single bonds. Then we have 1 hydrogen-chlorine single bond. We're going to subtract that from our carbon-carbon single bond. But now we have 5 times carbon-hydrogen single bonds. And then lastly, we have our carbon-chlorine single bond. Something you can do to make your life a little easier is I notice I have carbon-hydrogen single bonds and carbon-hydrogen single bonds, and we're subtracting them. So we can just go ahead and cancel out all 4 of these for our coefficient there, leaving 1 left. And this is going to simplify our problem a little bit as we can do quite a bit less math now. So condensing this, we have our carbon-carbon double bond plus our hydrogen-chlorine double bond subtracted from our carbon-carbon single bond plus our carbon-hydrogen single bond plus our carbon-chlorine single bond. Finally, I'll plug in the values, and I always try and save the values as the last step. 614 plus 431, these are all kilojoules per mole, minus 346 plus 414 plus 324 kilojoules per mole. Again, getting these from table 12 of our data booklet. And when I add this all up in my calculator, I get a delta H value of negative 39 kilojoules mole inverse. So hopefully this helps you understand how to approach problems with bond enthalpy and a little bit about what bond enthalpy is and how we use it. Anyways, have a great day.